talk my result in this workshop. Today I'd like to talk about robust privacy-preserving set intersection with quasi-linear complexity. This result is collaborated from Professor Jeong Chun and Professor Stanislaw Jarecki. I note that the part of this work is done when I visited UCI. In this talk, I'm only interested in the multi-part case set intersection and only the security against malicious adversary who can do anything arbitrarily. Now I'd like to explain the why privacy presumed set intersection is needed. Let me explain very simple application. In some situation, the CIA wants to know the passenger list of the American airline has a terror list. In this case, CIA just says send the passenger list to the American airline, but American Airlines say no, it's a violation of passenger privacy. In this case, the privacy presumed set intersection can be a good solution. After interaction, PPSI protocol just return the terrorist and passenger list intersection, and this Hyungtae is not actually terrorist. He is here. Where is Hyungtae? And both parties know the set intersection result. However, both parties don't know the other information about the list. And this is the outline of this talk. At first, I'd like to explain the previous result by Kisuna and Song. And then I briefly explain our goal and our ideas. And then, as an intermediate protocol, I explain PPSI HBC protocol, and then PPSI MAL protocol is our main protocol. In this protocol, we improved the online complexity. After that, in our main protocol, I'd like to show our protocol satisfying some property called robustness. Robustness means in robust protocol will output desired result even if the corrupted players' malicious behaviors are detected. In non-robust case, if malicious adversaries' anomalous behaviors are detected, non-robust protocol will not output the desired result. This is the difference of robust protocol and non-robust protocol. At the last, I'll explain how to improve local computation. I said our previous protocol satisfying has some property. Property means linear complexity in online pairs. However, local computation is still quadratic. So at the last, I'll explain how to improve local computation. Kisuna and Song proposed the first PPSI protocol more efficient than general multiparty computation. Thereafter, Sang and Shen improved Kisuna and Song's result with respect to the complexity in the number of players. In complexity, there is two important factors, the number of players and number of private sets. In our protocol, we only focused on the complexity in the number of private data. As you can see, all complexity has k-square terms. So all previous works complexity is quadratic in the number of private data. member? I'm sorry. Lambda is a security parameter. Let me explain the idea in KS protocol. I just say KS protocol for Kisner and Song's protocol. They use the polynomial to encode private data. To encode private data AI, they use polynomial like this. This polynomial has each private data as roots. The merits of this representation is Z intersection can be expressed like this. Ri is random polynomial and Fi is private polynomial of each player I. Then this is equal to this. GCD from Fi to Fn is same to the private polynomial of set intersection set. So the Kisner and Song's protocol, the goal is that all players compute this polynomial together without leaking information about Ri or Fi. Let me explain the detail of KS protocol. EPK is an additive homomorphic encryption supporting the threshold decryption. And we define encryption of polynomial as a tuple of encrypted coefficient. At first, each player I computes Fi, after then encrypt Fi and broadcast with some generality. This generality means proof of plaintext knowledge. After then, every player is known encrypted polynomial of each private polynomial. Then each player I choose random polynomial, and then using homomorphic property of the encryption EPK, each player computes this and broadcast along with this. Then every players have this encrypted polynomial. Then using homomorphic property of EPK, let's compute this and decrypt by using threshold decryption protocol, and then extract all roots of this polynomial. This capital Rj, every player is contributed to the random polynomial chosen by himself. So even if we let all of the numbers are n, even if n minus players are corrupted, in the view of n minus 1 players, this polynomial capital Rj is still random polynomial. So, as I said, this polynomial is almost same to intersection polynomial. So, this protocol output the desired result. But this protocol has two weak points. One is the expensive computation. Expensive computation is depending on this computation. This computation means product of two polynomials. They used to encrypt polynomial, they used a tuple of encrypted coefficient. So this computation requires quadratic in the degree of polynomial. This is one weak point. The other weak point is this protocol is non-robust. Non-robust means they use the generality property, generality protocol. But generality only guarantee that if adversary behaves anomalously, we can detect that behaviors. However, if the corrupted players behave anomalously, this protocol should stop, and excluding the players, this protocol should restart. So this is non-robust protocol. our goals are two. One is the quasi-linear complexity and robustness. To obtain quasi-linear complexity, we propose point representation. Each dataset is represented by a set of points over a polynomial having private data as roots. Then, the multiplication and addition of two polynomials require just linear number of operations in degree of polynomials. This is our first key observation. Then, to obtain robustness, one may think verifiable secret sharing is can be a solution for the robustness. However, if we use the usual verifiable secret sharing, there occurs some problem. Precisely, usually in additive homomorphic encryption, the message is located in the exponent. If you consider the Fourier encryption, you can easily know what I'm saying. And then, in usual verifiable secret sharing, the shared message is also located in the exponent. So, if we use usual verifiable secret sharing to share encryption, the message should be located in the exponent of exponent. In this case, it is hard to prove about the statement for the message. In our protocol, each participant is required to prove that his shared encrypted polynomial is well formed. But if we use usual verifiable secret sharing, it is not easy. So we propose new verifiable secret sharing, supporting efficient construction for zero-knowledge proof on shared encryption. Now I explain the point representation of private data. Let Xi be the data set of player Pi. We define private polynomial of Xi same as Kisner and Song's protocol. Then we define point representation of Xi by pairs of points and values of according values of f, where S is a public set of size larger than or equal to 2k plus 1. If we use this point representation, the point representation of product polynomial is easily can be computed like this. And point representation of polynomial can be computed like this. So this computation requires just linear operations. So this is our key observation. Now I explain the cryptographic tools used in our protocol. The modified Elgamal encryption. The modified Elgamal encryption is very similar to the original Elgamal encryption. The only difference is in modified Elgamal encryption used G to the M as instead of message M itself. If we use the modified Elgamal encryption, the decryption algorithm does not support a complete decryption because we have to solve the DLP to obtain message M. However, it is enough to our protocol. I'll explain later why this is enough. The modified Elgamal encryption satisfying these properties: additive homomorphic property, semantic security, distributed key generation, and threshold group decryption. And to obtain robustness, in our protocol use the Pedersen verifiable secret sharing. I'll not explain the detail of Pedersen verifiable secret sharing. However, I think the audience can follow the remaining talks even if they don't know about Pedersen verifiable secret sharing. PPSI HBC protocol is almost same to the Kisner and Song's protocol. However, the difference is we use point representation. So in the main expensive part is this polynomial product. So in our protocol, we can reduce this part to linear. At the end of interaction, the each players obtain g to the fs. As I said, we use the modified Elgamal encryption, so each players obtain end of intersection the g to the fs instead of fs. So, but by using polynomial interpolation, obtain g to the ai, where fx is ai xi. Then, for all alpha in private set, test g to the f alpha is equal to 1. 1 means identity of the group. If g to the f alpha is equal to 1, alpha is an element in the set intersection. Otherwise, alpha is not. This process takes quadratic operations. So in online phase, linear complexity is achieved. However, still quadratic in local computation, and this protocol is not robust. To obtain robustness, we propose new verifiable secret sharing. To share encrypted polynomial, first dealer choose the random CS and compute this and broadcast. After then, share CS by using Pedersen VSS. This is the sharing phase. And to reconstruct the encryption, just reconstruct the CS by Pedersen VSS reconstruction algorithm. After then, compute this, and by using homomorphic property, compute this. Then each player can reconstruct the encryption of F. Very simple verifiable secret sharing protocol, but this protocol has a very useful property. We can construct a generalized proof protocol for shared encrypted value, because the shared encryption preserve the simple algebraic structure. And in the security proof, the simulator can equivocate on encrypted polynomials, since Pedersen verifiable secret sharing allows to equivocate CS. This is very useful in security proof. This is our main protocol. Almost same to the previous protocol. The difference is 1, 2, 3 steps in online phase. At first, verifiable secret share encryption, and then generalized proof for each player's private FI is well formed. And then reconstruct encrypted polynomial. If malicious adversary leave the protocol after proving the step 1, the remaining players can reconstruct encrypted polynomials. So even if malicious adversary leave the protocol, this protocol can output the desired result. This table shows the complexity in each step. In the last phase, we obtain the linear in K, but in input conversion and output conversion, we have still K-squared. The reason why we have K-squared in local computation is we use the expensive polynomial arithmetic. In input conversion, to transform data set to point representation, we have to use polynomial interpolation and polynomial evaluation. Similarly, in output conversion, we have to use polynomial interpolation and evaluation. If we use the usual polynomial interpolation and evaluation algorithm, the complexity is quadratic in the degree of polynomial. To improve local computation, we can apply fast Fourier transform for fast polynomial arithmetic, such as polynomial interpolation and polynomial evaluation and multipoints. If we apply fast Fourier transform to our local computation, we can reduce each computation from k-squared to quasi-linear. Then, is FFT appropriate to our protocol? We have to check. Usually, FFT uses a primitive 2 to the nth root of unity, such that 2 to the n is larger than 2k. K is the degree of polynomial, and it is same to the set of the size of private data. The existence of primitive 2 to the nth root of unity is equivalent to that p minus 1 is divided by 2 to the n. To find such a prime, p is equal to 2 to the n times r plus 1. This is typo. For a random integer r, we should test at least log p because of distribution of prime. In this case, r should be larger than log p. So, m should satisfy this equation. But we know the 2k is much smaller than p. So, in our protocol, m satisfying the condition this. So, we can use FFT in our protocol. And even if 2 to the m divides p minus 1, the semantic security of Elgamal encryption is guaranteed by DDH assumption. Especially if we use elliptic curve Elgamal, then there is no non-generative attack to DDH assumption. So, to apply FFT to our algorithm, our protocol, we have to use prime p, such a prime p this, but the form of this prime does not affect the semantic security of our protocol. This table shows our result. We obtained the quasi-linear complexity and robust property. As a further study, quasi-linear complexity in all parameters, I think quasi-linear complexity in all parameter means even if our protocol attained quasi-linear complexity in the number of private data, still quadratic in the number of players. So I think if you can obtain linear complexity in all parameters, it will be very good. Similarly, if we can find or construct efficient protocols for other set operations, such as set union or set threshold set union, I think it will be a good, it will be an interesting problem. And last, I'm very interested in the functionally complete set operation. Until now, there are several set operation protocols. However, the almost protocols support only 1 or 2 set operations. So the applications very restricted. However, we can construct functionally complete set operation protocol. I think it will have a very numerous applications. These are references cited in my talk. Yeah.